In this video, we're going to look at a problem dealing with the concept of optimization. So, with optimization problems, we use information that we're given to create a function in terms of a variable. And what that function aims to do is either maximize or minimize a certain value. And how we come up with that function is we use the relationships given to us in the problem between variables that we can come up with and construct and other things that we make out of the problem with drawing diagrams and all that kind of stuff. And then once we have that function, we go ahead and we take the derivative of it because we know that from our knowledge in calculus, if we set that equal to 0 or solve it where it's undefined, we can solve for where the original function that we have has a maximum or a minimum, hence giving us an optimized value for what we were looking at in our problem. So now that we have the general scope of optimization problems, let's look and see what our problem tells us. So it tells us that we are moving into a new apartment and want to carry a curtain rod around a corner joining two hallways. We must carry the rod horizontally, and if one of the hallways is 8 feet wide, so I denoted it with this one, and then the other hallway is 5 feet wide, we want to find the length of the longest curtain rod that can be carried around the corner. So there's that keyword longest that tends to lead us to the fact that we're going to maximize the length of this curtain rod, but then I also really emphasize that it says that that can be carried around the corner. And so after we get into some more of the setup of this question and kind of look at the derivative and everything, I'm going to get back to that concept of whether this is actually a maximization or a minimization problem. But before I get to that, it'll be kind of easier to explain it after I've set up the relationship between our two known values and what we're looking for. But what we're looking for is we want to know the length of this curtain rod in some form or fashion, right? So what I did was I drew this right here as a little diagram, and then we'll call this, our length is L. So this is going to be the length of our curtain rod. Okay? And so, well, what do we know from this picture? Well, we know that we have a hallway of 5 feet and a hallway of 8 feet. So what we can do in this picture is we can draw some right triangles inside of this picture to incorporate those hallway lengths in terms of areas that are closer to our curtain, right? Because we know this is 5 feet, so that means that this little chunk of hallway right here is also 5 feet. And we know that this hallway is 8 feet wide, so that means that this part of this triangle is 8 feet wide. So we have a right angle here and a right angle here, and those are by construction, right? We can just, wherever this curtain rod meets this wall here, we can draw this straight down, perpendicular to the other side of the wall, and similarly, but going horizontal for this piece. So in this problem here, I've kind of highlighted points of contact here with the curtain rod and the different walls, and it's kind of where we get our triangles from, where we just drew our triangles at. And the reason why I do this and why it lends itself to a maximization or minimization problem is that you know how when you're trying to move furniture, in this case a curtain rod, around a corner like this, you want to try to fit the longest piece of furniture around that corner, and the best way that you can do that is by barely grazing this wall to where you can still kind of swing past it, and do the same thing here. So whatever you swing here can still be swung over there by grazing the wall while also keeping in contact with this, and this allows you for the most range of motion to kind of pivot this piece of furniture around. So what we're going to end up finding is that we want to keep these 3 points of contact with our piece of furniture in relationship to the walls that we've made for this hallway throughout this problem, and that'll kind of set up why this is either a minimization or a maximization problem as we discuss that later on. So now that we have these two triangles created, I kind of want to look and see, is there anything else that we can use to tell us to be able to relate these hallway lengths and the length of this curtain rod? Well, we have a right triangle here, and we have that in this triangle, this chunk of the curtain rod, we'll call this chunk Y and call this chunk X. So we know that the length of the curtain rod will ultimately be X plus Y, right? We're just kind of further dividing it up into other variables. But if we were to create an angle measure here, this theta, we can find length Y by figuring out what this theta is and then using the sine function, right? Because sine of this theta angle is equal to the opposite side measure over the hypotenuse measure. And then similarly, we're going to use the same kind of idea for this triangle, but we're going to use this angle. And the reason for that is what's the relationship between this angle and this angle? If we call back to geometry, what these two are, they're vertical angles. And we know that vertical angles are congruent, right? So vertical angles are congruent. So we know that this is actually theta while this is also theta. These two are the same angle measure. And to find x, we don't have the opposite side measure, but we have an adjacent side measure. So we can make a relationship between theta and x by using cosine of theta equals 5 over x is the adjacent over the hypotenuse, right? So let's go ahead and write that down and see what we have for this problem so far. So we said that sine of theta equals 8 over y, and then we also said that similarly cosine of theta equals 5 over x, right? Well, now we want to put this in terms of x and y to be able to solve for length, right? And so how we write these two functions in terms of x and y is we simply need to switch the spots of the denominator of the fraction on the right side with our trig function. Because if we want to solve for y in this case, we're going to need to multiply by y on both sides, or multiply by x. So we get that we have y sine theta equals 8, or x cosine theta equals 5. Then we just divide by cosine theta. So instead of doing those two long drawn out steps, simply it boils down to switching the spot of these two. So here we're going to write that this is y equals 8 over sine theta, and this is x equals 5 over cosine theta. And we can also rewrite these using the reciprocal identities of these functions, right? So we get 8 cosecant theta, and we get 5 secant theta. So now what have we done? Well, we've made a function for our length in terms of this theta angle, right? So let's go ahead and write down what we have so far and see what we need to do from this point on. So we have that L of theta equals, and then we said it was x plus y, right? But we know that x is 5 secant theta and y is 8 cosecant theta. So we have 5 secant theta plus 8 cosecant theta. So this is our L of theta function right here, and this is what this function is going to tell us is that our length is depending on this variable theta. So after we can figure out what this theta is, we can very easily figure out what our length is by plugging that theta value into our x and y functions here that are also in terms of theta, and then plugging those values into L equals x plus y to figure out the length of our curtain rod. So we have a general strategy in place for this problem. Let's go ahead and look at what happens now that we need to take the derivative and find the critical points for this function. And the reason why we're going to derive and find the critical points of our original function is because we know from calculus that we've learned kind of recently that when we find the critical points of our function, those are where local maxes and min values are, which are in this case going to be the values that we're going to use to kind of optimize that length that we're concerned with for our curtain rod, right? So if we can set the derivative equal to 0 and solve for the theta value that either maximizes or minimizes this curtain rod, which we will get to here in a second, we can figure out what the length of our curtain rod is based, or like the optimized length of our curtain rod is rather. So let's take the derivative of this function. So we have the derivative of L with respect to theta. What we're going to get is that the derivative of secant theta is simply secant theta tangent theta. And then similarly, the derivative of cosecant theta is negative cosecant theta cotangent theta. That's why I changed the sign to a negative. So we have 8 cosecant theta. Let me go ahead and change that. So we have negative 8 cosecant theta cotangent theta. And this is our derivative function here. So I've been teasing everybody with the fact of like whether this is a minimization or not, a maximization problem for a while now. But now that we have our derivative, I kind of have to address what we're doing. So we know that critical points occur when derivative equals 0 or undefined, right? Well, in this context for our derivative, what makes this derivative undefined? What we really have here is we have 5 times 1 over cosine theta times sine over cosine theta minus 8 over sine theta times cosine over sine theta, right? So what we have is we have a lot of divided by sine theta and divided by cosine thetas. So if we get one of these trig functions to be a divided by 0, meaning that either sine theta or cosine theta, actually I got those backwards, so either cosine theta or sine theta evaluates to 0, we're going to have something divided by 0, meaning that we get an undefined value for our entire derivative. But where does sine theta and cosine theta equal 0? Where do those happen? They happen at 0 and pi over 2, right? Either the positive x-axis or the positive y-axis. And the reason why we're not necessarily going to be concerned with the values of 0 and pi over 2 is because if we were to say that our theta angle here was something like, let's use the case of 0. So if we want to get something that our theta angle is very, very arbitrarily close to 0, we're going to get a curtain rod that looks something like this, keeping those 3 points of contact in mind of the hallway problem. We'd have a point of contact here, point of contact here, and a point of contact here. But we know that if we try to swing this curtain rod in this hallway, the natural constraints of the hallway are not going to allow us to swing that curtain rod into this next hallway, right? So we know that we don't want a theta value of close to 0 or 0 for that matter, because it means that our curtain rod won't fit. And then if we use that same thinking, but taking this theta to be closer to a value, say, of pi over 2, we're going to get a similar curtain rod that looks something like this. It just gets very long and extended this length because we need to keep these 3 points of contact in mind. And once we do that again, we can't swing this curtain rod this way because, and we can't really have gotten to this point so far if we were going this way because we would have been hitting the wall the whole time. So say we're moving into this hallway, we couldn't swing this long portion of the curtain rod into this hallway. So what that means for us is that if we exclude values like 0 and pi over 2, the natural interval for our derivative function and for what we're dealing with in general for theta is we're going to say that theta is going to be an element of the interval 0 to pi over 2. So what that means is that our angle is going to be something between 0 and pi over 2. And we don't even necessarily want it to be something that is close to either of these endpoints, right? Because we saw that as we get closer and closer to these endpoints, the curtain rod will by nature become larger and larger to keep those 3 points of contact in mind. So that means that we won't be able to swing it. So what this turns out to be is that following the constraints naturally that we have of our problem, this turns into a minimization problem. Because what we're going to end up finding is we want to figure out where the derivative equals 0. We're going to ignore where theta equals undefined because, or where our derivative is undefined rather, because what that'll involve us really doing is figuring out the longest curtain rod possible that could fit that theta constraint, but it won't fit around the swing of our hallway constraint. It won't fit inside of the hallways for this problem. So we want to find the smallest curtain rod that we can get around this corner while also being the longest one that can touch those walls. So it's very an optimization problem that's more minimal in nature because we want to optimize it to be able to touch the walls, but not to be the longest curtain rod possible, as we saw with examples of 0 and pi over 2. And since sine theta and cosine theta are 0 at 0 and pi over 2, and those are being excluded from our interval, all we're really going to be concerned with is where the derivative equals 0. So what we're going to do is we're going to set this derivative equal to 0, and then we're going to solve for theta to figure out what our optimized point is, or our optimized value for theta is, so that we can figure out what the lengths of the x chunk and the y chunk of the curtain rod are, so we can add those together and find the length of our curtain rod. So, without further ado, let's go ahead and start that process. We have 0, 5 secant theta tangent theta, minus 8 cosecant theta, that was horrible, cotangent theta, like this, right? So once we have that these two are equal to 0, what I'm going to do is I'm going to move this whole term to the other side of the equation and set them equal to each other. Okay, so what we have now is we have that 8, or cosecant theta, it's a lot of C's and S's in here, I'm getting confused, equals 5 secant theta tangent theta, right? So I don't know about you guys, but I am much more comfortable dealing with sines and cosines and manipulating them as opposed to things like cosecant, cotangent, secant, and tangent. So let's rewrite this equation that we have in terms of sine and cosine. So here we're going to get 8 times 1 over sine of theta times cosine theta over sine theta equals 5 times 1 over cosine theta times sine theta over cosine theta. Okay, so now what we're going to do is we're going to multiply these together into one fraction on each side. So here we're going to get 8 over sine theta times cosine theta over sine theta. So we're going to get 8 cosine theta over sine squared theta, right? After we multiply all that stuff together. Then similarly on the other side, we're going to get 5 sine theta over cosine squared theta. Or, forgot the squared. I think it's squared theta. Okay, so now that we have a proportion here, we have a fraction equals another fraction or a ratio equals another ratio, what we're going to do is we're going to cross multiply these things here, right? Because what we want to do is we want to kind of get rid of these fractions but preserve the function's equality. So what we're going to do is we're going to multiply the denominators of each fraction of both sides, and what we commonly refer to that as is cross multiplying, right? So what we're going to do is write out that cross multiplication. So here we're going to get that 8 cosine cubed theta equals 5 sine cubed theta. Right? So this is what we got going on so far at this point. And then now what we're going to try to do is we want to get the trig functions on one side of our equation and the constants on the other. So what we're going to do is I'm going to say I want to move cosine cubed over here, because if we do sine cubed over cosine cubed, that evaluates to give us tangent cubed, right? As opposed to dealing with cotangent, and we're more familiar with tangent. So let's move cosine cubed theta to the right side of the equation. So we divide this away, and we're also going to divide 5 to the other side, right? So we're going to move the constants to the left side. So all we're doing is we're doing all that in one step. So here we get 8 over 5 equals, and then sine cubed over cosine cubed gives us tangent cubed theta, right? Well then, how can we take care of this cube? Because now essentially what we're doing, now that we've gotten something like this, we're trying to solve for theta. So let's take care of this power first. Let's take the cubed root of both sides to deal away with that cubed power. So what we're going to get is that the cubed root of 8 over the cubed root of 5, because if we have a quotient inside of a radical, we can write that it's the quotient of the different radicals of the numerator and the denominator, right? So we can kind of split this up into each term. And so now we're going to get that this equals tangent of theta. Well, now that we have that theta is the argument of a trig function, how do we undo that trig function? Well, we do its inverse, right? So we take tangent inverse of tangent, and it cancels away right there. It undoes itself because they're inverses. So what we're trying to figure out is that theta is the tangent inverse of the cubed root of, and I'm actually going to write cubed root of 8 as 2 because we know that to be true and just having to deal with one less cubed root. So we get that 2 over the cubed root of 5, the tangent inverse of that gives us theta. So then what does theta evaluate to be? Well, theta comes out to be approximately 0.8634. And there's some other decimal point values after the 4 here, but I'm going to go ahead and stop it at 4 because I feel like that's good enough for us for what we're writing. But in terms of my calculations that I do in this video and in the calculator, I'm going to keep all those decimal place values for as long as I can. So what we have is that theta equals 0.8634, and then this is in radians, mind you. We want something like this. This is going to be the angle measure that optimizes the curtain rod problem as we have talked about so far. And so now that we have found the value of theta, that gives us a derivative value of 0, or that allows our derivative to be evaluated to 0 rather. What that means is we have found the theta value that returns a minimum for us in our original function. So what was our original function but 5 secant theta plus 8 cosecant theta? So this theta value here is the value of where our minimum value happens for our function. And that's what we're looking for, right? Because we talked about how this problem is going to turn into a minimization problem of all the stuff that we're dealing with all the constraints that we're dealing with. We want to find the shortest curtain rod that we can get around the hallway, basically. Not shortest as in we can easily fit, say, a 2-foot curtain rod around that corner, but we want to find the longest curtain rod that still fits inside of those constraints. So we're not trying to find the longest curtain rod in general. We're still trying to minimize that length given those natural constraints that we have of the hallway, right? So we have found the location of where our minimum occurs. It occurs at approximately 0.8634 radians, right? So then, now that we found theta, we remember how earlier we talked about x and y as in terms of that theta measure, right? So what we need to do now is we need to figure out what x and y exactly equal, and then once we figure that out, we can figure out the length of our curtain rod. Okay, so we said that length equals x plus y, or length equals, and then we said that x is equal to the function 5 secant theta, and this was plus y was 8 cosecant theta, right? Well, now we know what that theta value is, right? We know that's 0.8634 radians. So here we get that L is 5 times secant of 634 plus 8 cosecant of. So now what we have is we have an expression here on the right side of this equation that we can plug into the calculator. After we let our calculator do some work, what that allows us to see is that the length of our curtain is approximately 18.2195 feet. So this is the length of the longest curtain rod that we can have to fit around our corner given the constraints. So again, we talked about how this is essentially a minimization problem in realm of the constraints of the problem. Because we weren't looking for the world's longest curtain rod that we could try to make fit around that corner. Because if we tried to get that and we tried to maximize the curtain rod length, we're going to end up with a problem of not being able to swing around the corner because we're going to end up hitting the wall and not being able to move. What this length of curtain tells us is that a curtain rod of this length will allow us to keep those 3 points of contact with the walls, but we are allowed to keep moving, and we can kind of keep swinging past those points of contact and get around that corner. If we have something like a 19-foot curtain rod, it's going to hit the wall and get stuck. It's not going to be short enough for us to be able to move around the corner of that hallway. So that's why we ruled out the values of theta being 0 and pi over 2. That did end up making the derivative an undefined value, right? If we plugged 0 or pi over 2 into this derivative, it would return an undefined value. But we didn't want that because even if this derivative evaluated to be undefined, what happens if we plug theta equals 0 or pi over 2 into, say, this form of x and y? If we plug or theta equals 0 into this equation here, what we're going to get is that sine theta evaluates to 0, so the y chunk of our curtain rod will be undefined. And similarly, for if we plug pi over 2 in for the x value of our or for the theta in our x function, rather, I'm getting tongue twisted, is if we plug pi over 2 into there, we're going to get that the x chunk of our length is undefined. And if we add something to undefined, it's still not going to change the fact that it's undefined length. So we still wanted to actually find a length. So if the whole minimization versus maximization part of what we've been talking about is a little confusing, just think about it in that light. If we were to plug 0 or pi over 2 in for this theta, it would give us an undefined length for that chunk of our curtain rod, and we can't have an undefined length. We know that the curtain rod exists, so we need to come up with a length in some form or fashion. So that's why we resorted to only finding the point where the derivative was 0 inside of this interval that we made here. Okay? So we looked at a problem, a rather lengthy problem with a lengthy explanation. This is going to be kind of a long video here. Talking about optimization of a variable or a value, right? So with optimization, what you need to look for is you need to figure out what you're trying to optimize, and then look at your givens, and then see if you can draw a picture or create a diagram or create a relationship between all the unknowns and the givens that you have and what you're looking for, and see if you can relate them in terms of one variable. Because what we're trying to do is we're trying to figure out, we knew that the length could be divvied up and we had these different hallway values, but by the use of theta and trig here, we were able to relate the whole length of the curtain rod in terms of x and y into different functions that related them in terms of theta, right? So we ended up making a function in terms of one variable, we see down there. We took the derivative of it, went through a lengthy discussion of the derivative equaling 0 or being undefined. We went ahead and solved for the critical points of our function, found it, and then we were able to figure out what the optimal length of our curtain rod was that could be carried around this corner.